Entonces pasamos a la siguiente presentación, que se refiere a la miniaturización de la tecnología de muros colados. Va a estar dada por el ingeniero Alexander Blatt, de la firma Bauer. Alexander, bueno, estudió ingeniería en la Universidad de Coburgo y se especializó en geotécnica, sí, tráfico e hidráulica en la Universidad de Leipzig. Desde 2015 se desempeña en Bauer en el departamento de desarrollo de métodos, liderando proyectos tales como este que nos va a presentar, el Cube System y Falcon Project. La presentación, entiendo, va a estar en inglés. Como saben, ustedes pueden acceder a la traducción simultánea a través de un icono que está en la parte baja derecha de la pantalla. Entonces, Alexander, please, you can start with the presentation.
Dear ladies and gentlemen, thank you very much for having us, me and my colleagues from the Bauer Maschinen GmbH in Germany. We are really happy to introduce to you the new Bauer Cube system. My name is Alexander Blatt, and I'm a member of the Method Development Department within the Bauer Group. In terms of the limited amount of time we have, I think we should start right away. You can see here a small agenda for the presentation which is coming up. After a small introduction, you will see all the technical data of the Cube system itself. Then I will talk a little bit about the process, working with it, and give a small outlook into the future. So for those of you who aren't familiar with the diaphragm wall process, these are the working steps you will need to perform to create a continuous wall. First of all, you will need a pre-excavation, which is responsible for the cutter to be able to work. Then the cutter is able to cut the panels, so-called primary panels, to the final depth. Then in the next step, the installation of the reinforcement can take place. And as a last step, for completing this primary panel, this panel will be concreted. After a series of primary panels, the so-called overcutting takes place, and the so-called secondary panels are constructed. These secondary panels fulfill the wall, and in the end, you have a continuous wall with a watertight joint construction. Here you can see 3 pictures of standard diaphragm wall equipment. You can see 2 standard machines on the left and on the right, and 1 low headroom application in the middle. In this picture, the low headroom application fits under a bridge, but you can also see that both other machines are in confined space situations. On the left side we have in a job site city, and on the right side the wall was constructed from a dam crest. So if we look at the idea of the cube system and where the idea was born, we have to look at the global trends and developments we're facing. I mean, urbanization, electrification, sustainability, those are words everybody is familiar with. And of course, this influences also the construction industry. And there is a demand for new equipment, and there is the demand of equipment with minimum footprint, minimum height, and minimum emissions. With these global trends, we have to face the fact that there will be the need for new infrastructure in the future. There will be the need for new underground parking space, underground water retention systems or water supply systems, but also new underground energy storage. So as you see, there are numerous applications which will be needed in the future, and all this space is limited because existing structure normally hinder the construction of such huge infrastructure in the moment. And we think that with our GNU Cube system, we can provide a solution for at least some of the projects which then might become possible. But if you look at the past and you try to find job site examples that overcame those challenges, for example, installing a wall from below existing structure, you will find a job site like this. This is a job site from Brussels from around 10 years ago. And here you can see that the personnel excavated walls manually by hand down to the final depth. Of course, if you look at the pictures, you can see that there's a high risk for the personnel, for example, of falling objects or even falling down. There might be the presence of harmful gases, and also, of course, a huge danger of a collapsing trench or the collapsing working area. So this is not state of the art anymore. Despite that, even if there isn't any huge collapsing trench or whatever, there might be long-term health problems due to the non-economic conditions the worker are in. So the question was, why did they do it like this? They did it like this because they had no real alternative to it. And that's why we at Bauer thought, okay, this is not state of the art anymore. And this is also one reason why we developed the cube system for right now. Further, this is also not a solution for every situation, because if you think of a water level which is above that wall or in that wall, then this method here by hand is not applicable anymore. But also at the Bauer Group, the construction of a wall from outside a tunnel, from inside a tunnel is not new. In 2003 in China, a cut-off wall was constructed from inside of a tunnel. The wall depth here was up to 78 meters, and they already worked with the overcut joint as well here. The problem is the normal low headroom machine needs to fit into the tunnel, so the tunnel needs to have certain dimensions. And not even the machine needs to fit in, also the supply lines needs to be fit in that tunnel cross section. There has to be electric supply, ventilation pipes, slurry concreting lines, everything you need to secure successful excavation need to be led to the trench. And that leads us to a tunnel cross-section dimension from around 6 meters in width and 6.5 meters in height. So, as a reminder, working with standard diaphragm walling equipment needs a lot of space. And this is where the idea was born to minimize the system. This idea wasn't started with Bauer alone. It was a cooperation with a Belgian tunneling company, Denys, which have over 60 years experience in their field. And we from our side provide the experience and the knowledge in terms of cutting. And that led to the cube system. We have it right now. So what is the cube system? The cube system is basically a diaphragm walling machine, but it's integrated in three 20 feet containers. You can see here the main components of the machine, which is a cutting unit, a pumping unit, the winch unit, and then the hose handling systems for the hydraulic hoses and the mud hose. What's new with the cube system? To be able to fit it into these dimensions, we needed to separate the cutter. So we have a cutting unit and a pumping unit, which will be connected before the work starts. Therefore, we need a pre-excavation where we can lower the first part, so the cutting unit, and then we move over the second part, the pumping unit, and then connect those parts together. And then we have a cutter which is able to work. But as you can see, we have only proven components we also use for other machines, but just in a new arrangement. If you look at the technical specification of the cutter, I want to point out two things. Because of the limited amount of time, I don't want to read out all of it. The length of the cutter compared to a standard machine is 2.4 meters instead of 2.8 meters. And the second thing I want to point out is, despite the small height of the cutter of 3.6 meters, we have 8 steering flaps integrated to ensure a high quality in alignment. If you look at the hose drum system, the hose handling system in the back, one information is really important here, and that is the depth capability of the whole system. Currently, we have a depth capability of 40 meters because of the minimum bending radius of the mud hose. Of course, when working in such confined space environment, the process needs to adapt as well. Of course, we need a slurry circuit to ensure that we can keep the trench open during the excavation. The cutter pump is bringing the material, the loosened material, to the separation plant where solids and slurry are separated. The KBKT pump brings the clean slurry back to the trench. So this is a slurry circuit we also have on any other job site using the diaphragm wall equipment. So this is also proven technique and nothing new for the cube system. Of course, the storage of the slurry, the separation plant, and the pump, they need to be placed outside of the tunnel if you're working in a confined space environment. But before we start cutting, you can see that the equipment needs to be positioned over the trench, of course. Here you can see that we have the solution that we are moving on a rail system, which is integrated in the working platform on this testing job site we made in our yard. We move by a hydraulic fed cylinder and a clamping device. So the clamping device is holding onto the rail system, and the cylinder moves the container in position. Here you can see it again. In a second step, we need to connect the cutter and the pumping unit, as I already said. Therefore, we need a pre-excavation of 1.5 meters, where we can lower the cutting unit and then move over the pumping unit and connect it together. This you can see here. We can lower then the cutting unit into the beer excavation. We move over the pumping unit and we connect both parts together by bolts. After the cutter is connected, then the system is able to work as a normal cutter and is then able to excavate the material. The cutting process itself and the installation of the reinforcement and the concreting is shown in this animation. And the animation starts with the same approach you already saw right now. We have a connection of the cutter, then the cutter is able to excavate a primary panel, needs to be disassembled again for movement, and is moving then to the next primary panel. In the meantime, we have a separated concrete and reinforcement cube, which is independent of the cutter, and through that container, reinforcement cages, of course, they need to be adapted in height to the container, can be installed, and the concreting process takes place by using a drummy pipe system. And with that system, we are then able to move forward and excavate a series of primary panels and then come back and do the overcut joint construction, which creates us a continuous wall. So those are the working steps you already saw in the beginning of the presentation. This is state-of-the-art technique in diaphragm walling. On this side and on the next two slides, you will see some impressions from our test site in Arising we performed to assess the whole process in this confined space environment. Here you can see the separation plant where the material is separated from the slurry and how the material looks like when it comes out of it. Of course, a constant measurement of the slurry parameters is key for a successful excavation. For the installation of the reinforcement, we use a coupler system. So this is an easy and efficient way to link all the cages together. Of course, the cages need to be adapted in height to the dimensions of the concreting container. The small lifting device helps us moving the cages inside and for the connection. For the last step, we use the drummy system for the concreting process, and we use the concrete pump for the transport of the concrete to the trench. Because if you think of a tunnel, and we simulated a tunnel in our small site, then of course the transport by mixer trucks is not possible. Here, of course, the control of the consistency of the concrete is important to ensure good transport of the concrete. So what's the outlook? What do we think becomes possible with the cube system? In our opinion, the cube system is giving opportunities for projects which weren't realizable before. If you look at current, or if you look at tunnels that recently have been constructed in Germany, you can see that the cube system mostly fits in everything we have constructed so far. So this creates opportunities of installing walls from inside of a tunnel and does not influence the daily life above it. So we think that underground construction in inner cities can become possible in the future, especially there where you need the infrastructure. So you don't have to have long logistics ways and lose money and time. So we think we have an innovative solution which is able to fulfill also economic reasons in terms of long-term utilization of that new infrastructure. But also, if you think of situations above the ground, we think that also the cube system is not limited for underground construction, but also can be used in above ground applications. So imagine you want to construct a new metro line under an existing main road in an inner city. So normally you have to have a huge impact on the daily traffic, but now with the cube system you are able to only minimize this impact on the daily life because you're able to work from one lane. And this brings up new opportunities and also new chances for projects in the future. And with this outlook and with this thought, we want to all thank you for the opportunity to show you our new innovative system. And of course, we are happy to get some feedback of you guys and also to answer your questions. And again, thank you very much and enjoy the rest of the conference. Thank you.